In today's video, we're going to introduce and work a little bit with arrays. This is just going to be a brief introduction, so ensure that you're reading along in the chapter. It's a relatively short chapter as well, but just make sure you're reading along in the chapter to help look at some additional code and some additional examples. So what is an array? Well, it's really just a single variable that we can use to hold multiple values. And so while we have that concept in C or C++ or any of the other higher level languages that we use, the same thing holds in assembly. What it really boils down to, though, is that we have a contiguous block of memory and that we use that memory to store data. And what we have in a high level language, let's take C for example, or higher level anyway, higher than assembly. What we have with C is the ability to access those elements directly. We can use the name of the array and then the brackets and then the index in order to access an element that we want. What we have in assembly or what we lack in assembly is that ability to directly access that element, and we have to calculate that address ourselves. And so we can do that by knowing what is the base address of our array. So what is the address of the first element, what are the number of bytes for each element, and then what is the index that we want to access. And I'll go through a couple of examples here that will hopefully clarify exactly what I mean by that. So first, how can we create an array? Well, we can create it in the data, the BSS section, we can create it on the stack, and we can also create it in the heap. And I won't spend much time talking about creating it in the heap. We would do that with something like malloc. We will take a look at an example of defining that in the stack as well as BSS and data sections. So in the data sections, you're going to, very similar, I mean essentially what we've been doing when we've been declaring our strings in there is declaring an array of characters. So we give it a label and then we use the directive define byte, define word, define dword in order to allocate the number of, essentially the number of elements that we want. How much total memory are we looking for? We can also use a macro called times, and times just gives us kind of a shorthand way of defining more memory for an array. And you'll see here an example straight out of the book how to do that. Although I won't bother to do that in any of the code examples that we'll look at today. The next one is in the BSS section, and that's going to be uninitialized. So using the res-b, res-w, so reserve byte, reserve word, reserve dword, same thing, right? We can use that in order to initialize or gain access to memory for an array that we're going to use later on in our program. It's uninitialized though, so in the data section we need to provide values. In the BSS section we don't provide any values. And then the stack, how we're going to get that space is by subtracting from ESP. So we decrement our stack pointer. We make room on top of the stack in order to use that space for our array, just like we would any other local variable that we've talked about when we've discussed locals on the stack. So here's some examples from the book, and you can see that the first ones are arrays defined in the data section. So A1, A2, A3, A4, all of those are just labels, array 1, array 2, array 3, array 4. The first one is an array of dwords, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we would look at that as a 10 element array, and each element of this array would be a dword. So that means that each element would be 4 bytes. Typically when you create an array of integers, for example, an integer is 4 bytes. So this would be very equivalent to that. A2 is 10 words, all initialized to 0, set to 0. Each element would be 2 bytes, or word size. Okay, array 3 is declared using times 10 dword 0. So that's that macro we talked about earlier that essentially says repeat or allocate dword, initialize it to 0, and do that 10 times. So A3 is equivalent to A2. Okay, and then A4 is another example, times 200 bytes defined byte 0 times 100 defined by 1. So that defines an array of bytes with 200 zeros and then 100 ones. Okay, as far as the BSS section, right, you can see here very similar, except that what we're doing is, or what we're not doing is initializing the values. So an array of 10 uninitialized double words, res D, and then a 6 is a res W, so word, so 100 uninitialized words. Okay, so what I really want to focus on today is one-dimensional arrays and how do we access that, because I said earlier that there is no direct way of doing that. There is no way, as in with C, where we can just use the square brackets in order to give us that index into that array. So we have to compute that address. So if you look at this as an example, array 1, array 2, define byte, define word, and then each array has 5 elements. So array of bytes, array of words. Well, how would I get, in this example, array 1, we move that into AL. Okay, and so what is that doing? Well, array 1, this represents the address for the base of our array. So if we dereference that and move that into AL, that's like getting the first element of that array. Okay, if we want to get the second element, well, then we have to add from that base 1, because this is an array of bytes. So this would be the first byte, this would be the second byte. And adding to 1 to that base address gets us to that next element. And so array 1 plus 1 into AL would be like accessing the array at index 1, or the second element. And so you can see this continues and goes through this through all these different arrays to give you examples of how, starting with that base address. And that's the thing that you're going to see consistent throughout all of these examples here, is that array 2, array 1, that points to the base of our array. And we're using that and then adding values to it based off of the size of the array in order to calculate offsets into that array in order to get to the different elements within that array. If we look at example on line 5, we move into AX, well, before that, example 4, move into AX array 2, right? Array 2 is the base. AX, we're using a larger register because these are all words, right? 2 bytes in size. So moving that into AX, array 2 into AX gives us the first element in the array, so the element at index 0. Well, let's get to the second element, we have to add 2 to that. So the base address plus 2, move that into AX, right? Because these are 2 bytes in size, that gives us the array's second element, or the element at index 1. Right? And so that's really important to understand. The book talks a little bit about multidimensional arrays, and I guess I just don't want to spend a whole lot of time on those. So just take a look at that in the book. Maybe later on in the semester I'll come back to it. But there's a formula for it, and really all it boils down to is a formula. Multidimensional arrays, if you've ever done that in something like C or C++, oftentimes this is the syntax to do that. Define an array of ints that is 5 elements, and each element is an array of 7 with 7 elements. And what you're getting and how that's going to be laid out in memory is still a linear set of addresses. And so you'll have 5 times 7, so 5 elements, each element of 7 elements, because they're an integer. This is an integer array, a 2-dimensional integer array. Each element is going to be 4 bytes. You're going to take 5 times 7 times 4. And then you can use this formula that the book goes through a couple of examples in order to determine how would you get the index for the array. Let's say we wanted to get 0, 1, or 2, 6. The book goes through an example using this formula in order to help you to calculate that. And then also talks about using larger dimensions. So you can review that. And then on the stack, how do we allocate space on the stack? Well, just exactly like we allocate space for our local variables. Once we're inside of our function, and we've executed our prologue, then we have to subtract from ESP the number of bytes that we need. So X is the number of bytes that we need for the array plus all the local variables. And so that's what we're going to see here. And again, I'm going to go through an example in just a moment. Okay. All right, so let's look at this. Here you can see I've declared array 1, and I defined that as an array of D words, 0 through 9. So that's a 10-element array. I have array 2, and I don't actually think I ended up using this. No, I didn't. So just an example, like you saw in the book, and that this declares an array of D words, 10 elements. Using this array 1, what this first little bit of code is going to do is it's simply going to iterate over this array and print off the values. So you'll see here as I enter into main, I move 0 into ECX, and then I move the base of my array into EDX. Okay, so now EDX holds that address. From there, I have this loop. And what this loop is going to do is it's going to print the integer. So I'm going to move each element of the array into EAX, print that value, print the new line, and then increment ECX and jump back to my loop. So this loop is set up to give me the 10 iterations that I'm looking for. What do I move into EAX? Well, as you can see here, what I'm doing is I'm calculating based off of the base of that array. So I don't use EDX anymore. I made some modifications to the code, so I'll get rid of that just so there's no confusion as to why I did that instruction. So what I'm doing then is I'm using the base of the array, array 1, I'm adding to it ECX times 4. Well, what is ECX? ECX is our counter. What is 4? 4 is the size of each element. I made this an array of D words. So we're going to, every time through this loop, we're going to start with the base of the array and then take it times, we're going to add our counter times the size of the element. So when it's 0, we have array plus 0 times 4, which is 0. So we have just the base of the array. Well, now to get to the next element, we need to add 4 to this base address, okay, because each element of the array is 4 bytes wide. So the next iteration, ECX is going to be 1. So we have array plus 1 times 4, which is 4. So that gives us the next element of the array. Okay, next iteration through, base of the array plus ECX is now 2. 2 times 4 is 8. And that's how we want to walk through those addresses, 0, and then 4, and then 8, and then 12, and then 16, right? And this is a quick and easy way to do that because we have a counter variable in our register ECX. And so if we multiply that times the size of the array, then that allows us to quickly and easily calculate those addresses. And what you'll see here, I'm going to save this and run this code, at least this first portion of it, right, that prints off our values 0 through 9. Right, so we walk through that array, starting at the first element, moving to the end, and printed off those values as we went. Okay, what happens if that is an array of a different size? So let's say array 3 is a D word, and we have the same elements. 4, 5, 6, 7, 8, and 9. Okay, so what's different? Well, the size of the element is different. Here's a D word, 4 bytes. This is a word, 2 bytes. And so what that changes is how I calculate that address. So let's do the same thing, except let's print off array 3. So if I move into EAX, array 3 plus ECX times 2. Call print int, call print new line. Let's save that and run. Ooh, yikes-os. That's not what we're looking for. That's why, because I'm not using a D word, so that would be word. Oops. And that should be the appropriate size as well. There we go. Sorry about that. Okay, so here we can see the results. Okay, so I had to change everything, which I failed to do initially, because the array size, the element size, is now word instead of D word. So I'm changing my calculations. I'm multiplying by 2 because the size of those elements is 2 bytes instead of 4. I'm saying start at this address and only give us, a word size, only give us 2 bytes of data out of memory, and move it into AX, not into EAX. And that were some of the mistakes I was doing before, is that I changed this from, I was trying to read a D word and move it into EAX, which worked, but based off of my calculation, I was reading more of that array than I should have. Next thing I did was I made this from D word to word, but I didn't change the register that I was moving into from EAX to AX, so there was a size mismatch. So once I corrected that, now you can see that everything works as expected. Okay, so that is being able to understand how to identify that this is calculating the element of array, and being able to do that is going to be pretty important. All right, so I'm going to go ahead and just comment out those prints. Okay, what about just an individual element? Well, what we can do is it's very similar to what we looked at previously. Let's say that I want to get the first element of the array. Well, I move into EAX, I dereference array 1, and that moves that first element. Right? We're back to this array being essentially an array of D words. Excuse me. And then we're printing new line. Okay, so I'll save this and you can just see the output. That should print 0. Okay, well, what if I want to get the last element of the array? Okay, this is a 10 element array, so I would want to get array at index 9. So how would I do that? Well, each element is 4 bytes wide. So if I take 9 times 4, that gives me 36. So if I say array I plus 36, then that will give me access. That'll calculate the address for the last element of that array, right? Which is what you're seeing here. So this first print prints the first element, which is the 0. The second one prints the last. And then this third print is printing the element at index 8. So this is the 10th element, this is the 9th element, index 9, index 8. Okay, same thing, right? Array plus 32. So the 8th element, so times 4 gives us 32. So that's how we can calculate that address, calculate that offset. Okay, comment these out. All right, the last thing that we're going to look at then is calling this function printArray. And it's going to look relatively similar to this previous example. The only difference is going to be that I'm going to allocate space on the stack in order to first initialize this array and then just simply print off the values. So what's going to be different is how I calculate the element of the array. So first thing that you'll see in this function is a prolog. So push EBP, move ESP, EBP, and then I'm going to subtract from ESP 30 hex. And how many elements would that be? Well, if I take 30, and let's just say I'm going to make this an array of ints. So if I take 30 and divide that by 4, that, oops, by 4 gives me C, or 12 elements. Okay, so I have up to 12 elements in this array. That is how much space I've allocated on the stack, considering each element 4 bytes in size. Okay, the first thing that this is going to do is it's going to initialize each element based off of our counter. So I'm just going to increment from 0 to 11 and then move that value, that counter value, into the array. So let's start with ECX is 0. First thing, compare ECX to 12, and then jump if greater than or equal to the end of the loop. Otherwise, I'm going to move into this element of the array the value of ECX. So what this first example is doing is it's calculating based off of ESP. And this is not as commonly done, but I just wanted to show you as an example how to do it. So ESP is the top of our stack. We've now subtracted from our stack pointer 30 hex. So ESP is the top of the stack. So we're going to start at that address. That's going to be the base of our array. And we're going to go from that lower address to a higher address on the stack, right? Because the stack grows from higher to lower. So ESP plus 4 times ECX. Well, ECX is initially 0. So 4 times 0 is 0, plus ESP gives us the base address. Okay, so that's going to move the value of ECX into that first element. Then we increment ECX, jump back to the compare. All right, so we won't jump out of this loop for a little while yet. So now the next iteration, ECX is 1. So very similar to the last example. 4 times 1, ESP plus 4 times 1. So 4 times 1 is 4, ESP plus that is 4. So that moves us to the next element because each element is 4 bytes wide. Next iteration, ECX is 2, ESP plus 4 times 2, that's 8. So ESP plus 8, and we're moving ECX into that. So that's how we're calculating based off of ESP, each element of the array using that counter variable to help us do that. Okay, once that loop is done, we've initialized every element of the array. So we have 12 elements initialized with values from 0 to 11. Next thing that I'll do then is just simply walk through that array and print those off. Okay, the only difference in this loop and the previous is now I'm going to use EBP in order to determine where is the base of my array to access those elements. And so you're going to see yet another way, and this is going to be probably the more common way, that if you see a, for compiler generated code, if you're looking at that compiler generated code and there is an array in a function, so it's using the stack, if it's using the stack anyway for the space for the array, this is more than likely how you're going to see it done. So we'll zero out ECX, we'll do the same loop. So we're going to increment from 0 to 12, and then once we get to 12, we're going to jump, break out of the loop. The only thing that's different here is that I'm going to move each element into ECX and then print that value and print a new line. So what do we move into ECX? EBP minus 30 plus 4 times ECX. Okay, the 4 times ECX is the same. Each iteration we're taking 4 because that's the size of our array times ECX, which is our counter. So that's going to give us a calculation for each element. That's going to allow us to walk through each element of the array. What I'm using for the base address though is EBP minus 30. Right? In this example, ESP was the top of the stack. And since the only thing I have allocated stack space for in this function is my array, then we have just ESP. If I wanted to use EBP, then I would just subtract 30 from it, because EBP is our base pointer, right? Higher to lower. We've now allocated space on the stack, so ESP is at a lower address than EBP. So in order to get to that, I have to subtract from EBP minus 30. That gives us the base of our array, our local array. And then from there, I can add 4 times ECX. So you'll see this very frequently. If you take the reverse engineering course 444, you'll see this very, very often. And you'll need to just be able to quickly and easily identify this, and you will after you've seen it a few times and used it a few times as a calculation into an array. Okay, and then if we save and run that, you can see it just prints off every value of the array. So I've initialized it from 0 to 11, that's my 12 iterations, and then printed those off. Okay, so the code will be uploaded. Encourage you to take a look, make sure that everything is making sense to you, that the calculations and how to calculate the different elements of an array make sense, and certainly let me know if something does not make sense or if you have any questions. That is all I have, and I will talk to you guys in the next video. Thanks.